Okay, so for today, we are going to discuss some kind of a new topic about the diffusion models. So at the very beginning, if we discuss some kind of the pros and the cons of the diffusion models, kind of the one of the some of the kind of the advantages of the diffusion models is that we can really get some kind of the high quality outputs and also the diversity in the generation, also with some kind of very stable the kind of training the process. You already implemented like DDPM and the DDIM, and we have seen that actually the training is basically not that difficult, and also the implementation is basically not that difficult. So there are kind of like many other advantages in the diffusion models. And also in the diffusion models, we are having some kind of the iterative the process in the generation. And every step in the denoising the process, we can add some kind of the guidance in terms of that we can do some kind of the conditional generation, and we can also do some kind of synchronization. So these are also basically making another kind of the advantages of the diffusion models in terms of that the pre-trained diffusion model can be applied into some kind of the multiple the applications. So these are kind of good things of the diffusion models. But the downside of the diffusion model is that basically it involves some kind of the multiple the denoising steps, as we also have seen in the previous the kind of the assignments and also the lectures. To get some kind of the high quality outputs, actually we need to have some kind of the more the denoising steps. So as we have some kind of the more the denoising steps, we can get some kind of the very good quality of the outputs. So I guess you already basically play with those kind of things. But if you basically use the DDPM for the image generation and also many other things, typically you will need to run in this kind of like from the 200 to the 1000 the denoising steps to get some kind of the okay the outputs, right? With the DDIM, the good thing is that now we can reduce the number of the denoising steps from the 50 to 200, which is still basically involving quite many kind of the computations in the denoising process. So when you think about like applying this kind of the generated models for many kind of some real the applications that we can do some kind of provide some sort of the AI service for some kind of the applications, the kind of the bottleneck might be is that how we can reduce the computation time and also the computation the burden in terms of that we can quickly generate some kind of the good quality of the outputs. So basically, the topics that we are going to discuss for this week and also the next week is basically how it's about how we can reduce the computation time while basically maintaining the good quality of the outputs. So these are some kind of the basically the plot showing some kind of the trade-off between the computation time and the quality. So the x-axis is the indicating the number of the function evaluations, the number of basically some sort of denoising steps. So obviously, as we increase the number of the function evaluations, we are decreasing the FID. Basically, lower FID means basically the better quality of the images, right? So we can achieve some kind of good quality with the DDPM, and you can see that if we can run it like 1000 times, DDPM is giving the best outputs, right? But if we have some kind of like limited some kind of a computation, the time or the burden, then we might want to reduce the number of the evaluations into the 200 or the 50. For those cases, we can see that DPM is not working that well. While basically DDIM is basically giving some kind of the better performance. But here the question is that only with some kind of the like 20 or 15 or the 10 number of the times, can you still get some kind of the good quality of the outputs, even with some kind of pre-trained diffusion models? So that's kind of the topic that we are going to discuss today. And for that, actually, for today, we are going to discuss some math involved with some kind of the SDE and the ODE. So I strongly recommend you to be prepared with the pen and the paper in a way that you can do the hands-on work, like understanding those kind of things. I think you'll need to basically do your own some kind of some exercise, those things, to better understand all the details in the DPM solvers. So basically, to discuss this kind of like the first generation, we are going to go back to some kind of discussions about like how we can basically see the link between the DDPM, the DDIM, which is basically designed for the discrete setup with some kind of the continuous setup diffusion models. So in the continuous setup, we could say that actually what we are doing with the DDPM, the DDIM is kind of like simulating the Langevin dynamics with some kind of certainty time steps, right? So what we also have seen last time is that actually all the fold process, the data, the perturbation, the process actually can be formulated as one of the stochastic differential equation in the continuous time, which is basically having these kind of terms. So as you can see in this equation, the xt here is basically indicating the function denoting the xt at each of the time step t. So now we can see each of the data, the trajectory that we are generating, basically the final the output, can be seen as the function of the xt, which is starting from the x capital T and then going to the like x0. And if we see all this kind of the path of the xt, that can be considered as kind of like having the a function over the time domain. So now we are basically finding a function that satisfies this equation. And the last point of each of the function becomes of our final output, right? So there will be multiple such kind of the functions mapping the data point in the prior distribution to the data point in the data distribution. So each of the trajectory becomes the xt here. And the derivative of the first derivative, the xt, the trajectory, has this kind of the form in terms of that the involving some kind of some two terms here. Like one term is called the drifting the terms, and the other term is called the diffusion terms here. So the first kind of the important effect is that every basically diffusion default process has some kind of the corresponding stochastic differential equation in the continuous time domain. So this is like the one important thing. And the second important thing is that if you also see the reverse process, basically mapping the x0 to the x capital T, this reverse mapping can also be formulated with another the stochastic differential equation. So especially for the fourth process, when the SDE, basically differential equation, is basically represented with the ft here. Sorry, the drifting coefficients ft and also diffusion the coefficient gt here. Then the corresponding the SDE for the reverse process has this form in terms of that. Now we are also having the ft here and also gt here and here. The additional basically term is basically the score here. So that's why basically we also basically discussed like, learning this course. So if we could basically learn this core, then we could basically solve this kind of the SDE in terms of that we are finding the xt, basically mapping the x, capital T to the x0, right? So the fourth process was mapping the x0 to the x capital T, and we are going to the other way around in terms of doing some kind of generation. And now also the noise prediction network was basically predicting the score with some kind of a scaling term here, right? So now we can also replace this score term here with the output of the noise prediction network with some kind of scaling term here, right? So this basically is something that we can try to solve in terms of like running the generation. Clear? So one more thing is that, so we have seen that like all the kind of the diffusion, the fourth process can have this kind of the SDE formulation, right? Then obviously here the question might be is that what's the FT and the GT here? And also what's the meaning of this like DW here, right? So we are going to see like one by one without some kind of like seeing all the details in the proof. So we are first going to see the meaning of this kind of like DW. This is basically adding some kind of stochasticity in the equation. So without this term, the whole equation becomes the typical differential equation, the ordinary differential equation that we can easily solve. But because of this term, we are adding some kind of stochasticity into this equation. So this basically DW, basically this term is basically called the Wiener process, which is also called as the Brownian demotion, which is basically a real valued continuous time the stochastic process, which is basically having those kind of following the properties. The first property is that it's always basically starting from the zero. So when the time is basically zero, the probability that the output of the evaluation of this process to be zero is 1. So that's the meaning of the like almost surely kind of like W0 is 0. So every like the trajectory we are starting from the 0. So that's the initial condition. And the second condition is that also the incremental, basically the changes from the time step the S to T is basically characterized into the normal distribution. So if we see basically the incremental changes from the time step S to T, you can see that these should follow the normal distribution with the 0 mean here. So this is the second characteristic. the third characteristic is that in every step, the increment at each of the time step is basically independent with like what we had in the previous the steps. So this kind of like the independent increments is another kind of characteristic. And the last one is that also the probability that the WDT, this process is to be continuous over the entire time domain. The probability for that is basically 1. So that's another kind of the properties of the Wiener process. And this kind of like Brownian motion has been used in the many kind of the other kind of the studies in the like, finance or some kind of physics and the chemistry kind of like many parts. And we are also seeing this kind of the Brownian motion in terms of seeing some kind of the stochastic differential equation that can also characterize our the diffusion process. So that's the meaning of like this dW term here. So that was the meaning of like this part. We're adding some kind of stochastic. Then also the question is that like then what's the basically the exact like the FT and the GT term here. So how can you also derive this kind of the FT and the GT term here? So that's the kind of the next question. So for that, actually, we are first going to see some kind of the general versions of the diffusion models. Actually, the DDPM, the DDIM that we have discussed in the previous lectures is basically some kind of special form of the more general form of the diffusion models. So actually, we can define some kind of the any diffusion model that is basically characterized with this kind of the full diffusion process. This is the full jump process that we termed before. By basically defining the diffusion process with this kind of the some Gaussian distribution. So for any kind of the Gaussian distribution, having this scaling term and also the variance here, if basically these two coefficients basically satisfy this condition, then you can see that this is kind of like one of the the diffusion models, like characterizing the process. So the only condition that when you define the scaling term and also the variance here is that so we call this as kind of a signal to noise ratio. So when you see the ratio between the scaling term and also the scaled of the variance here, when you see that this ratio is like monotonically decrease over time, then we can see that this is like one of the diffusion model that we can basically do some kind of the forward process and the reverse process. So this is like kind of the more the general form of the diffusion models. And we're gonna see that what is kind of some special case of like this. The DDPM and DDIM was kind of special case of this, right? And given this kind of the more the general the definition of the forward process of the diffusion model, so what we can see is that now we can basically find some kind of the corresponding diffusion model from the SDE. And also we can do the other way around. So let's think about this SDE, which is basically describing our the forward process in the continuous domain. Then given this kind of the forward process, the SDE, now we can find the forward diffusion distribution. You see the forward jump distribution from the x0 to the xt, which is defined with the scaling term and the variance here. And these two terms are now defined with respect to the ft here and also the gt here. So here the thing is that if we can have any kind of the SDE that describes the forward process in the continuous domain, then we can derive the forward jump distribution conditioned by the xt, conditioned by the x0 with the scaling term and the variance here, based on the ft and the gt here. We can see that there are some this kind of the relationship. See? So for any kind of the SDE, if you know the ft and the gt term here, based on that, we can derive the scaling and the variance term here. And based on that, actually, we can do the opposite as well. So now we just think about the case that now we are having the forward the diffusion the distribution, which is now defined with the alpha t and the sigma square t for the scaling and the variance here. And based on that, we can also find the corresponding the SDE using the same equation here. So it's basically a matter of like solving the ft and the gt here with respect to the alpha t and the sigma square t here. So if we solve the ft and the gt based on this formulation, then what we can see is that now we can do the other way around in terms of like finding the ft and the g square t using the given definitions of the alpha t and the sigma square t here, using the scaling and the variance here. So this is because showing some kind of the mapping between the SDE formulation for the fold process and also the fold, the diffusion, the distribution for the jump distribution. If you have like one of them, you can find the other based on this kind of the mapping function, right? It is clear. So you can do some kind of the exercise in terms of how we can find the other one, like finding the SDE from the distribution or finding the distribution from the SDE. And we can further basically also rewrite the G squared term in terms of the, since we are having the derivatives of the sigma squared here, right? So we can basically rewrite this term into this. And also we can see that actually the derivative of the sigma t is the same with this term. Because if you take the derivative of the log sigma t, then you're gonna basically cancel out this. Then you can see that these two are actually identical as well. So the whole purpose of like having this kind of the rewriting is that now we can combine these two terms because like we can see that both of them are having the same log term. In terms of that we are having the more simplified version here with the lambda t here. Yeah. So keep this in mind. We're gonna say this like lambda t in the rest of the slides. So the thing is that since the alpha t squared over the t squared, since this is like decreasing, when you also take the log of the alpha t over the sigma t, this lambda t is also decreasing. So we are just like introducing another d variable, which is basically decreasing over time. And we can also see that this g squared can be rewritten into this simplified form when you introduce the sigma t here. So we have seen so far like basically how we can find like the fold diffusion distribution from the SDE and also do the other way around. Basically, all about basically the mapping things, right? So this is kind of the some known facts that we are not gonna discuss like very much details. You can also check out some kind of the references here to understand the more. But we are going to see like so how these are basically related to what we have seen in the DDPM DDIM case. So actually, we have very briefly discussed this kind of point in the previous lecture, but actually we can see that the DDPM is kind of the special case of the general diffusion the model in terms of like having this specific default transitional distribution. So now this is like distribution from the not conditioned by the x0, but conditioned by the xt minus 1, right? But we also have seen that if we have the fold transitional distribution, based on that, we can also find the fold jump distribution as well, right? So now we are seeing some kind of a special case of the diffusion model by defining the fold transitional distribution defined in this way. So this was the case of the DDPM, which is what's called the variance preserving the case because the variance is basically preserved in the SDE formulation. Actually, the other case that we did not discuss that much is like this case. This is another kind of the some special the case of this some kind of the general diffusion models in terms of the now we are defining the full transitional distribution in the other way around. So basically having this kind of specific form, which is not having this scaling term here, but only have the variance here. So you can see that actually there are multiple ways to define the diffusion models. The only thing is that we just need to have some kind of default transitional distribution that satisfies this condition. The signal to noise, the ratio between the scaling term over the variance, this term should be basically monotonically decreasing. This is the only kind of a condition. And we can think about like multiple ways to basically define the some diffusion model. So actually the reason why this DDPM is basically famous is that this is basically kind of like well-known some kind of the special form of the diffusion models that is basically known as kind of like practically working very well. And also if we see the corresponding the SDE formulation, we can see that it's the case that the variance is basically not exploding over time. So that's also the reason that we are basically getting some kind of the good performance in the real cases. And also what you can see, especially for the variance preserving case, is that when you define the full transitional distribution in this way, based on that, actually we could see how we can also derive the full jump distribution, xt conditioned by the x0, right? So we have seen like how we can derive this distribution from this distribution, right? in the discrete setup. And also we can do the same thing in the continuous setup. So if you basically calculate this in the continuous setup, the one thing that we need to see is that now the beta t is not defined for each of the time step. We also need to think about that this is kind of the function over the time t, right? So this is also kind of like predefined function over time t that the user can basically define. So we can also control the beta t as we want, right? So given the function of the beta t, now we can say that the forward jump distribution can be basically defined with this kind of scaling term and the variance here. So given the transition distribution, now we can see the corresponding default jump distribution, which is defined in this way. Then if we also remind the things that about the beta t that we discussed in the DDPM case. So actually the beta was the function which is like monotonically increasing over time, basically non-decreasing function over the time t, right? So given these characteristics of the beta t, the function of the beta, and also basically definitions of the alpha t and the sigma square t, can we quickly check whether the SNL, the signal to noise, is also decreasing in this case? So this SNL should be decreasing so that this becomes the correct diffusion model, right? So we can quickly check whether the SNL is basically decreasing in this case. Can you answer like whether this is like decreasing or not, and also why this is decreasing? Actually, we can quickly go with this. I mean, the thing is that you can see that beta t is basically non-decreasing function, and we are accumulating the beta t over the time step t, right? So which means that like this integral is also kind of like increasing. But we are taking the exponential of the minus like this integral, right? So this should be basically this alpha t should be decreasing. And the sigma squared is basically defined as the 1 minus alpha t, which means that this should be increasing. Now this is increasing. And basically we are dividing the alpha squared by the sigma squared, right? Then the whole thing should be decreasing, right? So we can see that actually this definition of the specific diffusion model basically satisfies the condition of the SNL, which means that this is kind of like one of the correct, the way to basically define the one special case of the diffusion model, right? So yeah, so this is basically the one of the examples. So, and also we can check out like what's the corresponding the SDE in this specific the DDPM case. So from the previous slide, what we can see is that depending on our the definition of the scaling term and the variance here, we could basically derive the corresponding the SDE with this function of the ft and the g square t here, right? So which means that if we plug in the definitions of the alpha t and the sigma square t into these functions, we can also find the corresponding the SDE in this case, right? So can you also quickly try to basically find the SDE, which is corresponding to our the DDPM case? So actually this can be a little bit like complicated. So you can check out this later. You don't need to answer for now. But actually it turns out that like after like rewriting all the things, actually you can see that the corresponding the SDE becomes like these kind of like simplistic simple forms, like basically the FT, this becomes like one of the 0.5 times the beta t here. And the GT also becomes like the root of the beta t here. So you can also check out that because we are also finding relationships with the G security here. So we also need to have the just like GT here. So you can check out those kind of some details later. And also for some kind of there is also another way to prove this. You can also check out this reference in terms of like how we can also derive the corresponding SDE in this case. So basically the thing is that given the DDPM deformulation for the specific the definitions of the transitional distribution in this way, you can find that actually the corresponding DSDE is basically having this kind of form, which looks actually quite simple, right? So which means that if we can solve the SDE, this is also for the SDE of the fold process. And based on that, we can also find the SDE for the reverse process. And if we can somehow solve the SDE, basically finding some kind of function satisfying the SDE, then that will be basically some kind of the trajectory that we wanted to see, right? But actually, the problem of the SDE is that it is basically involving the Wiener process, which is basically making or some kind of the complication in terms of how we solve that kind of equation. But really good news in terms of that is that if we think about the SDE corresponding to some kind of diffusion models, actually there is already some kind of a corresponding the ODE, not having the Wiener the process, which is basically having the same the marginal distribution of the noise data point of the XT at every time step. So in this figure, what we can see is that these are basically some kind of the visualization of the trajectories that we computed using the SDE and also its corresponding the ODE. As you can see that these red curves are basically like jiggling like this over time because of the stochasticity. But the white curves here are basically generating some kind of the trajectories using the ODE corresponding to the given the SDE. So which means that since the marginal distribution of the XT is basically matches with the ones of the SDE in every time step, instead of like solving the SDE, actually we can consider solving that corresponding the ODE, which is also called the probability flow ODE. So that's kind of thing. So without seeing some kind of details, so actually what we are going to see is that actually given this kind of the reverse process, the SDE deformation, so this was the formulation we have seen before, right? And also we introduced some kind of the new notation of the variance here, which can replace this term, right? Then given this kind of like reverse process, the SDE, actually the corresponding the ODE becomes this term, which looks actually quite is the same, right? With some kind of small differences like having the two here, right? So which means that like we can think about like running the denoising process as we have done in the DDPM, the DDIM case. Instead of that, in the continuous space, we can also consider like solving the SDE of like this formulation in terms of getting some kind of the multiple trajectories like satisfying this equation, right? And instead of like this, actually we can consider like solving this ODE, which should become much easier because we are not having the Wiener process here. So that's kind of the basic idea. And especially for the variance preserving case, in the DDPM, the DDIM case, if we computed the corresponding the FT and the G security here, right? So if we plug this into the previous the ODE formulation, then actually we can see that it turns out to basically solve this specific ODE to run the reverse the process. Which is like all the kind of equation that we are with some kind of given the parameters for the alpha t and the lambda t or sigma t here. These are some kind of the given the parameters, right? And these are some kind of the outputs from the noise prediction the network. So if we can find some kind of the function xt that satisfies this equation, there's some kind of the desired outputs mapping the x capital T into the x0. So for all the differential equation, there'll give you some multiple functions. And the way that we can basically find, specify one of them is to basically have some kind of the boundary condition, which basically means that if we specify either the starting point or the end point or whatever point in the space, then we can specify like one function that satisfies the whole equation, which means that given this kind of ODE, if we basically specify the x capital T, the starting point in the inverse process, then we will be able to basically find the full trajectory from the x capital T to all the way to the x0 with all the noise data points and also the final data point. So actually what we can see here is that a kind of like quick summary at this point is that for each of the general the form of the diffusion model, actually we can find a SDE that describe the full process in the continuous space. So that's the first thing, right? And also the good thing is that also it's the reverse process can also be formulated with another the SDE. Okay? And also for all the SDE describing the diffusion the process, even we can also find the kind of corresponding the ODE that matches the margin distribution at each of the time step. So this basically means that instead of like running the reverse the denoising process with some kind of formulation that we have seen in the discrete the time steps, now we can consider solving the ODE in the continuous time step in terms of generating some kind of the data points. So that means that if we specify the any x capital T with this boundary condition, if we solve the ODE, then we will be able to get some kind of the final the output of the XU. So this is kind of the good news because there are tons of some kind of the numerical methods of solving the ODE. If you took the differential equation the course, then you know that like there are multiple ways that we can basically, if you put some kind of the coefficients in the differential the equations, this kind of some sort of the off-the-shelf tools will be able to automatically solve all the equations given the boundary condition. So which means that now we don't need to implement the denoising process ourselves. We can just use some kind of the ODE solver with some kind of the pre-trained denoise prediction the network in terms of generating some kind of functions that satisfies the ODE formulation. Make sense? So it sounds like it makes like our life much easier because we don't need to implement the denoising process. But actually, our goal for today was not to just basically solving the ODE formulation, but it's more about basically how we can solve the equation more quickly with some kind of few number of time steps. So the thing is that if we use any kind of some existing the numerical the ODE the solvers, the thing is that we can get some kind of the accurate results, but with some many time steps, more than 50 or something. But here the question is that since we know the specific the ODE formulation here, based on some kind of the characteristic like this specific the equation, can we make some kind of the dedicated the ODE solver for this specific equation in terms of that we can also get some kind of the accurate outputs with some few number of the time stamp. So that's the things that we are going to discuss for today. Make sense? Any questions on this? So what we can try is that now we know the reverse process, the ODE for the DDPM case here, right? So you can really consider basically implementing, like basically not implementing, even just like using some kind of the numerical solver of the ODE with this equation and see what you get. You can really try that and see that you should be able to basically get some kind of good results with some number of the time steps. That's what we can do. And the thing is that now we are going to go further in terms of like not using some existing ODE solver, but making some kind of the dedicated some solution for this specific equation. Clear? So for that, we are going to discuss a little bit some basics about the ordinary differential equation. How many of you took the differential equation course before? The mathematics department. So if you took the differential equation course before, the things that we are discussing today would be quite easy, very kind of like basic things. If you didn't take the course, it's okay. We are going to really discuss some very basic things first and slowly move on to some kind of this more difficult things. So for the remaining of the time, we are going to briefly discuss like how we can solve the ODE formulation for each of the specific cases. So the things about like the solving the differential equation is that we just need to come up with some kind of solution for each type of the ODE formulation. And we are going to start with some kind of the easiest case and go into some slightly more difficult case. So as kind of the simplest case, let's think about this case. So the first order linear differential equation. So we are just having all the kind of the good words, making this easier, like first order linear. So basically, this is the first order equation in terms of we are only involving the first order derivatives, not the second order, the higher order derivatives here.
And this is also the linear in terms of that we are having the linear term here. So here the linear does not mean that any of those functions are linear, but if we treat all these functions as kind of the variables or the coefficients, then we can see that actually this whole equation is kind of linear with respect to the xt, which is kind of the variable that we are going to find here. But actually this is also a function in this equation, right? So basically the trajectory of the xt, the basically noise data point over the time step t is basically the function xt here. And we are finding the function of the xt over the time domain t here with this kind of like linear term here, right? So this is like the most, basically the simplest the case of the differential equation. And let's even make it even like more like simpler in terms of that we are dropping the offset term here. So not having the qt here, dropping this part, and only having this kind of like the scaling part here. So given this kind of the simplest form of the differential equation, how we can find the xt that satisfies this? That's what we are going to see. And for that, while we assume that xt is not zero over all the time domain dt, we're going to basically divide the left side over the xt here. Then can you basically come up with like any kind of the some expression that is kind of like related to this part? So actually what we are going to do is that we are going to basically simplify this left-hand side with some kind of the another types of the derivative of the function. Then you should have seen this before in the calculus course. So which function, the derivative, like which function is basically matching this left-hand side? So based on your memory from the calculus course, actually, we can see that if we have the log function, log of the xt, and if we take the derivative of this log function, then this becomes same with this, right? So we are basically first taking the derivative, the log of the xt, so that becomes like 1 over the xt, and also the remaining term becomes of the derivatives, the xt itself, right? So we can see that actually the left-hand side becomes identical, or like taking the derivatives of the log of the xt, right? So now we can see basically how we can simplify the left-hand side. And since the left-hand side is basically the derivative of the function, what we can do is that we can simply take the integral on the both of the side. So if we take the integral on both sides, then we are having some kind of the offset term here, and taking the integral here. And we also need to take the exponential as well, taking the exponential on the both sides. Then we can see that the xt here becomes one of the functions, having the exponential the term here, while basically having some kind of the arbitrary scaling term c here. So we can have some multiple function xt with the arbitrary scaling term c here that satisfies the given differential equation. Make sense? So this is the easiest case in terms of that we can find the xt function from the given the differential equation. So let's quickly do some kind of the exercise with this simple example. So let's say like this is kind of the given the ODE formulation with this term, and then we are having the boundary condition that the x0 should be 1. Then can you find a function, the xt, that basically satisfies these two constraints? Yeah, we can easily say that it should be xt to the exponential minus 1 over 2 dt, right? So this is kind of very simple, right? So yeah, so this was the simplest the case. So now we are going to go into slightly more complicated kind of the case with like going back to the general form. So in the first order, the linear differential equation, generally we can consider having this kind of some offset term here, right? Which is kind of like sort of the constant term with the xt. And now we are going to go like one step further in terms of that this qt becomes the function not only the function of in terms of the t, but also function in terms of the xt as well. So this is the case which is called the first order semi-linear differential equation. In terms of that, we are having the linear term here, and we are also having some kind of extra term here, which may not be linear or the constant with respect to the xt, which can be any kind of the higher order function with respect to the xt. So this is like more complicated kind of case. So given this kind of more the complex the ODE function, how can we basically find the xt that satisfies this? So yeah, we are going to see the solution for this. And before that, let's recall the simplest case. So for the case that when we do not have some kind of the offset term here, then we have seen the solution here, right? And based on that, what we are going to do is that actually there are multiple ways to find the solution in this specific ODE formulation for the semi-linear case. But we are going to see the example with with some kind of technique which is called the exponential integrator, which is basically nothing but basically we are multiplying some kind of the exponential term on both the left-hand side and the right-hand side. And don't ask me why, but based on some kind of inspiration from the simplistic case, we are going to consider multiplying this term, this specific the exponential term on the left-hand side and the right-hand side. And at the end, we are going to see that multiplying this magically basically solves all this kind of problem. Okay. So let's see that we are multiplying this exponential term both on the left-hand side and the right-hand side. Then this becomes like this. Then actually the reason why we are multiplying this exponential term is that now this whole looks kind of like complicated, but actually we can easily simplify the left-hand side. Based on this fact that if we take the integral of this integral, then it becomes like just like taking the pt here, right? And also we are going to use another defect of the product rule for the derivatives. If we take the derivative of the product here, then we can say that it should be like this. I mean, it's like high school kind of mess, right? So based on those two facts, what can you do in terms of simplifying the left-hand side? So if we use these kind of two facts, the left-hand side becomes the derivative of this product, of the exponential term here and the xt here. So that's the thing. So when you basically multiply this kind of like exponential term, then all kind of the technique that we are basically using here is that we are making one side as kind of the derivative of a function here. In terms of that, now we can solve the problem by taking the integral on the both sides. That's also what we have done in the simplest case, right? Kind of like same thing. But it's basically matter of like by multiplying the exponential term here. So based on that, what we are doing is that we simply basically take the integral on the both sides, then because this becomes the offset term, and taking the integral here. And here specifically, we are going to set the s to be greater than t because we are basically discussing the reverse process. So we are going to get into that. But basically, we are taking the integral here, having some kind of the constant term with some kind of the specific the s here, right? Then we are having this. And at the end, what we want to do is that we want to find function the xt here, which means that we additionally need to divide the whole the both of the sides with this by this, right? So we multiplied this term at the beginning, and now we are dividing whole the terms by this exponential term. So we are dividing by this term basically means that we are multiplying this exponential term without the minus but plus here, right? The same thing. So we are dividing the both sides with this, which is identical to multiplying this exponential term with the plus here, right? So we can see that now the xt has this formulation. Okay. And one more thing in terms of simplifying this is that since we are basically having the integral of the same function with the different range, like one is from the t to t, t to t0, and the other one is basically t0 to basically s, right? So we can basically simplify this in terms of like taking the integral of the s to t. This is also the same in terms of we are taking the integral from the t to t0, and the other one is basically tau to the t0. So we can consider taking the integral from the tau to t. So this becomes the final, basically the formulation for the xt. So given any kind of the choice of the s here, depending on what we choose for the s here, we can have some kind of different formulation for the xt, which is having some kind of the exponential term here, and also the integral of the exponential term multiplied by the q, the nonlinear term here. So this looks a little bit like complicated, but you can see that this is basically using some kind of the technique that we have seen in the simplistic case. Make sense? So if this was kind of fast, then I recommend you to check out the slides after the lecture and see how we derive all the things. So based on this, let's do one more exercise. So now let's think about that we are not having the linear term here, but some kind of the offset here. We sense the same the boundary condition. Can you find the xt that satisfies these two conditions? So basically what we can see is that we know that x0 should be 1, right? So we can just take this s to be 0, right? So if we take this s to be 0, then we can say that the whole formulation becomes like this. And we can, from the definitions of the g, you can cancel these two out. Then we can see that the function looks like this. 1 plus t times the exponential term. The function looks like this. So yeah, basically based on this, you can now solve any kind of the first order, the semi-linear, the differential equation with any definitions of the f t and also the g, x, t, and t. So this can be non-linear, and this is kind of the scaling term for the linear part, right? So this was like very quick kind of the introduction for the ODE. And we are going to plug this idea into the formulation that we have seen in the diffusion, the ODE formulation. So let's get back to the ODE formulation for the diffusion of the models. So this was basically the ODE formulation for the variance preserving decays for the DDPM and the DDIM decays, right? So for the DDPM decays, we could see that the linear term, the scaling term becomes like this function. And also this is basically the nonlinear term. Why is it like nonlinear? Because we are having the noise prediction the network, which is taking the xt as the input, right? So our the noise prediction the network is also a function, and it may not be linear. Obviously, the typical linear network also involves many the nonlinear kind of the components, right? So because of that, we can say that actually this is kind of the nonlinear part with respect to the xt. So we can actually see that the ODE formulation, the probability flow, the ODE that we are seeing is one of the examples of the first order, the semi-linear ODE. So let's think about like solving this equation based on the things that we have seen in the previous slide, which will be basically simply plugging this PT and the QT here into the this equation from the PT and PT and the QT here, right? So let's just plug in here. It might look kind of complicated, but nothing but if we just plug in this like PT and the QT, then we can rewrite the ODE formulation into this way. And from the definitions of the lambda t that we have seen before, then now we can say that the ODE formulation becomes like this. Makes sense. And one more kind of trick that we are going to use in terms of like simplifying further this is that because like we are having the derivatives with lambda t here, which also looks kind of a little bit like complicated. So to eliminate this term, what we are going to do is that we are going to use the fact that the lambda t was kind of the decreasing function. So lambda t is a the strictly decreasing function over the time step t, basically means that there is the one-to-one correspondence between the lambda and t. For each of the lambda, we can specify the corresponding t, and the other way around, because lambda is basically decreasing over time, right? So because of like this fact, now we can consider having some kind of the inverse function from the time t to the lambda, which means that in this equation, we can also change the parameter of the time t into the lambda instead of taking the t here. So especially for the second term in the integral here, let's think about it now. We are replacing all the parameters about the time domain t into the corresponding the lambda. Okay. So then we are replacing the t here into the lambda t here, and also the s here into the lambda s here, and also the tau here becomes the lambda tau. Actually, this is kind of like same. We are just like changing the some kind of the notations and the some kind of the some kind of the parameters here. But basically for this, if you basically compute given the lambda tau, once you compute the corresponding the time step the tau, and just feed this into the noise potential the network, that becomes the same, right? So it's basically some notation wise, basically we're just changing the parameters from the t to the lambda. And the good thing is that now we can see that this cancels out. We can ignore this part. So after changing the parameters, we can see that the whole equation also becomes like much simpler into this form. Makes sense? So this becomes the ODE that we wanted to solve in terms of generating kind of data points. So it's the ODE method. Now how we are going to solve this specific the ODE formulation. Then since now it looks kind of like simpler, we can try to basically solve this by some kind of discretization. So let's get back to like discrete space from the continuous space in terms of like having some discretization of the time domain. In a way that now we think about that we are having the xt and the xt plus 1 and xt plus blah, blah, blah kind of thing into the x capital T, right? So this is basically what we have done in the DDPM denoising process. And let's say that now the S is basically the T plus 1, the next T time step. Then we can say that the noise data point xt can be computed from the previous the noise data point in the denoising process, which is the xt plus 1, with some kind of some integral form with the the noise that we are predicting within neural network, right? So given the xt plus 1, now we can compute the xt by solving this equation, right? So the whole thing is that now we are also having this kind of a complicated integral here. So how we can get some kind of the approximation of this kind of integral? The easiest way to handle this integral is basically assuming that this is only for the time step from the t plus 1 to the t, right? Which is basically in the lambda space becomes from the lambda t plus 1 to the lambda t. And we know that this range would be very small, right? Very small range of the lambda and also t. Very short range from the lambda space and also the time t space. So in this kind of very short the range of the lambda and also the t, the simplest way to basically approximate this is that we just assume that this epsilon will be constant over this kind of range. This is basically the first order approximation, assuming that the epsilon here will be constant in the range from the lambda t to the lambda t plus 1. Then what we can do is that we can take out the epsilon out of the integral here, while assuming that this is basically the constant. And the only thing is that we just need to compute the integral like this, which can be computed analytically very easily, right? Make sense? So with that kind of like the assumption that the epsilon is basically constant in this range, we can also rewrite this. Then now it looks like very like feasible to compute, right? After doing some kind of the rewriting multiple times, we can see that actually the xt at the noise data point at the time step t can be basically computed from the xt plus 1 with some kind of noise prediction, and also with some kind of the scaling term and the coefficients here, which are all based on the hourly definitions of the kind of the diffusion models. So given the xt, actually also what we can see is that this is basically identical with the noise prediction with the xt plus 1 and the t plus 1. So given the xt plus 1, we predict the noise here and compute all the things. Then this becomes the xt without any stochasticity. Make sense? So let's do the last exercise here for today. So we have seen that in the variance preserving the case, in the DDPM case, the alpha t and the sigma squared, it was defined with respect to the beta t here, right? And then now we can say that this becomes some kind of the first order approximation of the ODE formulation for each of the time step. So based on that, can you also describe the xt with respect to the xt plus 1 and the beta t? Okay, think about this question after the lecture. So you might just take some time to basically grab all the things. You don't need to answer this question, but try this yourself after the lecture. Before we see the answer of this question, actually the thing is that so this was basically the example that we are basically running the reverse process by solving the ODE without any stochasticity, right? And we have seen such kind of example before. What was the case? The case basically running the denoising process without the stochasticity was one of the examples for that was the DDIM, the deterministic sampling, right? In the DDIM, the deterministic sampling, we could basically make it this value to be 0. Then we could see that the xt minus 1 can be computed directly from the xt without adding any randomness, right? The very interesting thing here is that if we basically rewrite all the formulation in the DDIM, actually, from all the definitions of the diffusion models, actually we can see that this DDIM formulation is identical with the first order approximation of the solving the ODE. That makes sense. Yeah. So now we can see like how this DDIM is basically related to solving the ODE. So these are basically all related in this way. We have seen that DDIM is kind of the generalization of the DDPM case, which was the case that we can control the stochasticity. And we could get some kind of very good results with the deterministic sampling by making the variance to be 0 with the few number of the time step. But actually that was identical with basically solving the ODE formulation, which has the same marginal distribution at the time step t. And since we are basically solving the ODE formulation directly, not the SDE, we could get, and also with some kind of this kind of the derivation of like how we can solve that with some kind of the first order approximation. Now we can see why we can get some kind of the good results even with the few iterations. So this is kind of the connection between the DDIM and the ODE, the probability flow of the ODE that we have seen today. So this is kind of an interesting point. So I strongly recommend you to basically try to derive all the things in terms like from this formulation, if we apply those things into the specific the DDPM case. Sorry, the DDPM the case, whether this becomes identical with the deterministic sampling of the DDIM. So we discussed like all the formulation for the general form of the diffusion models. So we can see that how this is applied to the special case, the DDPM case. Okay. So this was also the example of the first order kind of approximation, well, which is basically assuming that this epsilon, the noise expectation, the output will be constant from the range from the t to the t plus 1. But what can you do in terms of like the higher order approximation? One of the way that we can do some kind of the higher order approximation is that we can do this kind of thing, which is the first splitting the range from the lambda t to the lambda t plus 1 into the half. So if we are having the lambda t to the lambda t plus 1, we first split the domain into this like half. Now running the first order the approximation, but getting some kind of the xt kind of prime or something that we are saying u here is kind of for this specific the first step. And at this point, we basically update the noise, basically recalculate the noise at this point. And using this noise, now we are using this noise as kind of the constant noise over the entire the domain and running the first order approximation again. So that becomes the second order approximation. How about the third order approximation? We can do this like one more time. We can dividing the space not into the half and half, but into the 1/3, and basically getting some kind, running the first order approximation for the first like 1/3, updating the noise, and also computing for the twice of the range and updating the things. So we can repeat those kind of things. And more formally, the way that we can derive some kind of exact formulation for the higher order approximation is to use the Taylor expansion. So we are basically representing the noise here with some kind of the Taylor expansion, with some kind of the order n here. And then we can just also plug in this into the equation. In terms of that, we are making this to be taken out from the kind of the integral here in a way that we can compute the analytic form of this equation. Then after some kind of the derivation, actually we can see that the higher order kind of the approximation can also be derived into this form by computing this kind of the Python here. You can also check out like whether this equation becomes the same with the first order approximation that we have seen in the previous slide when you plug in those kind of the terms here. So this is kind of like more advanced things. And the assignment 6 is basically converting your DDPM code in a way that you can now generate the data points using the DPM solver. So the first task is basically implementing the first order the approximation, and the second task is to implement the second order the approximation, which will be more complicated. So as I mentioned at the beginning of the lecture, the second task, implementing the second order the approximation, is the kind of the optional task. You can only implement the first order the approximation. So using this kind of the idea of like solving the ODE, what we can say is that compared to the DDPM and the DDIM case, especially when you use some kind of the higher order the approximation with the third order here, we can say that even with some very few number of the function evaluations like 15, 12, and 10, you can say that the quality of the output is already way better than the cases compared to the like running the almost like 100 times with the other kind of the denoising the process. So this was basically the idea that we are basically accelerating the denoising process, not basically seeing all the things in the same discrete time domain the denoising process, but first thinking about some kind of like connection to the continuous space using the SDE, and also is basically the corresponding the ODE, and solving the ODE with some kind of the based on some kind of characteristics of the diffusion the ODE formulation. So this was basically all the basic idea in terms of basically how we can accelerate the denoising the process. So this is the basic idea for the DPM solver. And actually, you can see that there are quite many recent research, which is about basically how we can further accelerate with some kind of very good accuracy of basically the quality of the outputs using the same kind of the diffusion models. And also the good things of like all this kind of the idea is that you don't need to also retrain diffusion models. You just need to use the pre-trained the noise partitioning network, but just like running the denoising process in a like different way. In terms of that, you can get some kind of the better quality outputs, even with the few number of the function evaluations. So this is also very interesting kind of aspects in terms of that. Using the same pre-trained the network, you can get even the better quality of the outputs with some kind of the different denoising the process. So I also strongly recommend you to check out the other kind of recent work in terms of that, how we can further accelerate this kind of the process. So this is kind of the end of the today's topic about DPM solver. We are going to discuss how we can implement this in the assignment 6. In the next week, what we are going to discuss is the flow-based model, which is basically involving some kind of the fine-tuning the process in terms of that we can also further reduce the number of the time steps for the faster degeneration. So we are going to discuss the flow-based model next week. Any questions on this? So yeah, the next Wednesday, we are going to have the hybrid session for the assignment 6. So I will see you next Wednesday. Okay, thank you. Bye.